Hello students, good morning and welcome back to Physics 102 lecture. In our previous class, we highlighted four fundamental forces of nature and then we saw that the influence of electromagnetic force is stronger than that of the gravity, and we subsequently explained three methods of charging based on electrostatics. If you remember, we talk about induction, conduction and friction force. Okay, so we have already finished with that aspect. But as physicists, we cannot just leave things like that. We have to measure it, we have to write it down on equations and formulations to predict exactly how these charges push or pull an object, or how these charges push and pull between themselves. Okay, so today we are going into very first quantitative part of the class related to electrostatics, and this aspect is Coulomb's law. Okay, this law was formulated by French physicist Charles-Augustin de Coulomb in 1785 using a highly sensitive torsion balance. However, this law is the bedrock of everything we will do for this course or for this fact. So it's good to start with the physical statement or with physical statements, because when we say law, we are talking about a guiding principle based on scientific facts. Okay, so the statement about Coulomb's law, or we can state Coulomb's law as in a form of it says the electrostatic force between 2 point charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them, acting along the line joining the charges. Okay, this is the statement. The electrostatic force between 2 point charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them, acting along the line joining the charges. Okay, so let's break this statement down into maybe components. Well, we're talking about 2 point charges. We have already explained the concept of charge and what it is, and we also describe the point charge in space. So when we're talking about 2 point charges, what is a point charge? What is a point charge? So ideally, when we talk about point charge, we are assuming that all the charge is concentrated at a single small mathematical uh, point in space. We can imagine it as infinite. Okay, so the concentration of a charge within that space in a particular point is what we refer as a point charge. Okay, so in other words, you can, or in analogy, you can assume a planet as a point charge with mass in the gravitational mechanics, as we have just previously explained, related to the gravitational force field. Now, the second component of the statement is talking about the directly proportional to the product of the charges. Okay, so if you double the charge of one object, you double the force. Am I right? If you double both charges, the force increases by a factor of 4 because you are dealing with two charges. So this is what we mean, the directly proportional to the product of the charges. And this law, however, it follows the inverse square law. So what do we mean by inverse square law? So if you push two charges twice as part, maybe apart, the force doesn't drop by half. It drops to a quarter of its original length. I hope you're getting my point. So if you bring them, for instance, if you bring, the separation, maybe you bring them 3 times closer, the force will spike by a factor of 9. So it will multiply by 3. Okay, so 3 times 3, it will give you 9. So now let's look at how we translate this physical statement into mathematical and vector formulations. So you can see from my slides, I have 2 formulas. So don't get confused. I'm just trying to differentiate between the mathematical and vector form of this famous law. Okay, so this is what we normally, this formulation is what we normally found in many textbooks in our, right from our secondary schools, even from the elementary physics notes. Everyone is aware about this law and you can state it clearly. But in some cases, dealing with a complicated situation where you have maybe like 2D or 3D layout of these charges, you have to use what we call the vector form. Okay, all right, so let me just explain quickly. We measure charge in coulombs. Okay, this the charge is measured in coulomb, and r is the straight line distance between the charges. Okay, measured in meters, and the constant of proportionality 1/4 pi epsilon naught is written and the value is given, and this is nothing but what we call permittivity of free space. Okay, permittivity of free space. So which represent how easily an electric field can permeate in empty vacuum. Okay, so the characteristics of this electric field within empty vacuum is the sole permittivity of it within a free space. Okay, this is I think this is the way I can explain it in a very simple form. So it is a number that you must record all the time for your problem solving exercise, and the value is given. Okay, 8.85 times 10 to the power of minus. It's very big. It's very big because about 9 billion newtons of force for 1 coulomb of charge separated by 1 meter. Okay, so this constant is a mathematical proof to why static electricity is so strong. Okay, however, scalar equations are good for solving one-dimensional problems. That is a straight line homework exercise you can adopt using the scalar equations. Okay, but real space is 3D. Therefore, we remember and we know that force is a vector. So it has both magnitude and direction. In this case, therefore, to solve 2D and 3D layouts of charges, we must write Coulomb's law in its complete vector form. Okay, so don't get confused. Some lecturers may use vector notation. Some will use a normal mathematical form of this Coulomb's law. These are the differences. Okay, so when dealing with a very complicated space, maybe like 3D or maybe 2D, so you have to use a vector form. Okay, now, okay, so we have already explained this briefly, and I'm sure you know the F stands as what? A force vector acting on charges, that is charge Q1 due to Q2. Let me show you this. I'm talking about this force, the vector form. This is the vector form. So 1/4 pi epsilon naught is the constant of proportionality. So this force is the force vector acting on charge Q1 due to Q2. So that is why you have 1 subscript and 2 here. Okay. Now, remember, a unit vector has a magnitude of exactly 1. So it does not change the numerical value of the pulse. So its main function in physics is to tell our equation which direction the vector is pointing in coordinate space. I hope you are getting it. So it doesn't change what the numerical value of our force. So you have to take note of this. Okay. So in a case where we want to visualize the direction of the pulse, how do we determine whether this pulse vector points inwards or outwards? So we look at the sign of our charges. Like charges, that is a repulsive force. We know about it when you have, forces that push the charges away from each other. This is a repulsive case. Okay, as you can see now here, this is what like charges. You can see the force uh, is what separated by a distance. But in the second frame, you can see that these are the alike charges, and they are attracting force due to Q1 to Q2 and force due to Q2 to Q1. This is the explanation if you want to visualize the force. So the force is repulsive in the first case. So, and we have also attractive on the second case. So their mathematical product is negative. Yes, it's negative. If we look at the diagram here, okay, this is pointing to the positive direction, and the positive direction of this force is toward the negative side of the charge. Okay, so there is a separation between them. Okay, now one important thing that I want you to remember, um, as I mentioned, what is important, you have to always monitor and clearly observe the post vector's points in form of direction. As I mentioned, is it inward or outward? So if it is inward, that means the force is pulling the charges directly towards one another. Okay? So let's talk about something very interesting here. I mean, if you notice this case, for instance, let's recall about our Newton's third law, which is, as you can see from my slides, is perfectly preserved. Okay, so the force, uh, you know, the force F1, maybe we can say due to the force on Q2, you can imagine the kind of what the impact. I mean, the force pull the charges towards each other, as you can see now. Okay, is pulling the charges towards each other. So from the Newton's third law, remember in every action there is what? Equal and opposite reaction. Okay, so no matter how large one charge is, compared to the other, there is a kind of relationship between their interaction within that space. Yes, there is an influence between that space. So let me be brief because it's just one slide I uploaded. Maybe I will upload the subsequent one maybe later. So to wrap up our lecture for today, let's read our points so that we can recall what we have explained for today. Remember, the electrostatic force always acts along the straight line joining the two charges. So whenever you are drawing your forces or your force vectors on maybe during the exams or homework exercise, you always have to start by sketching a dotted line connecting your two charges. Okay, your force arrow must lie perfectly flat along that dotted line. Okay, so it cannot be tilt up or tilt down or sideways. It is strictly radial. Okay, so now we have already explained the mathematical expressions in the form of vectors, form of the equations from our famous Coulomb's law. Okay, so now I think we are ready to face a scenario or a situation on how to handle a condition, for instance, or what to do when there are three or four or maybe even millions, charges acting on one point. Okay, in this case we will use what we call superposition principle to add up all these vectors. So superposition principle is our next lecture. Superposition principle, that is the acting of forces on a quite number of charges within a particular space. How do we resolve that? We can use superposition principle. So I will upload my subsequent lecture on how to resolve this case. Maybe if you are dealing with many charges, so how do you resolve the forces within that case? All right, I think for today, let's stop here. And if there is any question, you can also channel your questions in the group, or you can just contact me directly, no issue. Thank you very much. Have a nice day.